So, ich glaube Englisch heute. Hello everybody. Thank you very much for coming, listening to me. I will talk a bit about resilience. We will first talk about what resilience is, and I will show you a few patterns and also hope that you get some ideas also on the architectural and design side, how you can build your systems perhaps a bit differently than you did it for the last decade or something like that. That's basically the agenda. What is a bit general stuff, then how we drift into failures. We will talk about failures in general. We'll talk about a bit what complex systems are and what are some of the properties that complex systems have. Then we will go into several patterns for resilient design. The first part focusing more at the architectural level, the overall level. Would say a basic, a good extension that we have heard from Neil Ford this morning and the last talk. And going forward to more, what did it mean, or could it mean in practice? So I would hope that should be a quite good roundup on the topic. About me, I'm working as consultant for Trivadis, as you have seen. You will not show any more advertised, so be sure. I'm engaged in money specification on the Java side. I was the spec lead there for the money JSR, which is final since last May. I'm also worked a lot as architect and engineer in different areas, different companies, different sizes, and also engaged currently with the configuration project called Tamaya, the Apache group. So let's start with the topic of what's resilience. And for starting, I have chosen here to show you this one. There's a real expert in resilience, which will you now present what resilience basically is.
Somewhere along the line, you changed. You stopped being you. You let people stick a finger in your face and tell you you're no good. And when things got hard, you started looking for something to blame, like a big shadow. Let me tell you something you already know. The world ain't all sunshine and rainbows. It's a very mean and nasty place, and I don't care how tough you are, it will beat you to your knees and keep you there permanently if you let it. You, me, or nobody is gonna hit as hard as life. But it ain't about how hard you hit. It's about how hard you can get hit and keep moving forward. How much you can take and keep moving forward. That's how winning is done.
So that's one of the essence of resilience. It ain't how hard you hit, it's about how hard you can get hit and keep moving forward. That's fault tolerance. But just let Sylvester Stallone here be it, and go also and have a look at other areas of science, what resilience there is. For example, psychology. It's more on the individual ways, how you can adapt stress or things and adversity. Or ecology, where you have, for example, an ecosystems and you have catastrophes or something like that happen, you have to recover, and you have to recover relatively quickly, looking at the damage that could happen. Or material sciences, think of rubber that is absorbing energy. You can pull or push it or bend it somehow. It will come back to its original form unless it's not too cold. Or sociology. Similar stuff there, but when we look there we have additional stuff that's coming in, because a society is built up on many individuals that's making it up. Changes typically are slow. We see that very good in Switzerland with all the democracy and the votings happening. Things are moving, but they are moving very slow. in societies, we talk about learning, talking together, there is interaction, and of course there is also diversity and redundancy. It's not one human being. There is a lot that make up a whole society or a community. We can then go further to biology. Also there we have multiple individuals building up a population. We can even think of or look at how different populations geographically split it or interacting somehow together. How genetic exchange is happening over these kind of popularities, under which circumstances. What happens if also there catastrophes are happening, like fire destroying big parts of the forest, for example. And also there we have some kind of self-organization. Animals die as well as people die. They will be exchanged by somebody else taking over the rule. Or if they have illness or something like that, also there is, also our body has quite a good capability of self-healing. And in computer systems, often we have that. So the question is, why? Or why, what are some kind of the common aspects why we then drift into failures? Why failures occur? Or what is the essence of failures? First thing is, I would say we should think about the best case. That's the happy path. When we think of a software, when we build a software, we just build it like everything works perfectly. Everybody of my counterparts of my services will answer my requests. I will get valid results, valid data. Everything is fine. And often people build exactly the services that way. Of course, then there comes some signature that says throws XY exception. Oh, okay. I have to write a catch statement. Catch exception, log, severe, return null, for example. Seen that multiple times in every kind of context, or whatever you do there. But basically, it's not that is not real failure management, because you just say something happened, I don't make anything, I just log it out and hope that my caller is more intelligent than myself. Failure tolerant would be perhaps a bit more. But there is another thing to think about because of complexity of the system itself. What is then a good action to take in a certain situation? Or how should we organize a system that it is failure tolerant, especially when we talk about complex systems? Sidney Dekker here is one interesting person because it's not a programming guy. It's one that is more at home in the aviatics area, thinking about why accidents with planes happen and how they could be prevented, or what is happening while we get there into failures. And what he says, I think, is a good thing because it applies one-to-one to the complexity we have also in software systems, is that basically with all the connections we have between all the components, and that gets not simpler with microservices. Microservices, I support it, I find it a real advantage doing it that way and building systems that way, but it gets not simpler. You have connectivity, and connectivity creates its own complexity. And definitely reminding also that your mind is capable of keeping or managing 8 to, let's say, 12 things at a time in parallel. After that, you will start forgetting the first ones again. It's a real issue with complex systems because our mind basically is not built for managing that kind of complexity you have in our software systems. Nevertheless, we try to operate somehow these systems. There's another interesting concept, which is called operating at the edge of failure, where we have 3 dimensions. We have our economic aspect. We should operate things as cheap as possible. We have the overload, which means that my developer, they have 8 hours a day. They should also have time for their families and go home, something like that. And we have the failure part, where we want to have, we want to basically to prevent. Now, we have our operating point, which is moving around, and if it's across the left boundary, we have a failure. That's the theoretical thing. But the question is why? Because what we do is, of course, it's clear that the economic pressure drives us for efficiency. So it should then push the button in that direction away from that boundary. The same is for efforts. Most developers, that's completely normal, that's a good thing. They don't want to do the work twice or multiple times. And this pushes the bottom more and more to the left side. Of course, we have then things that we try to prevent, that the bottom, our operation point, is not moving too much to the left side. We do policies, we do tools, we have controls in place, analysis tools, whatever what we do. Testing is also a way. But nevertheless, when we are good, we are got back. That's the target. But nevertheless, we know all failures happened. And what we can draw here again is that kind of error margin, which is what we want, what we try to move with our policies and everything. And we try to keep the operating point right from the bold line, which is the line imposed by our policies, hoping that we will never reach the error margin on the left side. There is one smaller issue with that, because we know much about our imposed imaginary boundary that we have defined by our guidelines and policies, and everything is in place. But honestly, we know quite less or not much about where the real failure boundary is. And what happens is that we start here, for example. We end up something like here, everything is okay. Basically, we end up here, still everything works. There was no failure. And over time, we are approaching that margin, that failure margin, more and more. We do not know that this is the case because we effectively do not know that kind of failure boundary. And what we're doing here is the call for that is we are flirting with the failure margin. And sooner or later we would also then move automatically perhaps also that kind of imaginary boundary, because everything works fine so far. So there's no reason to be that severe with all our policies. And then it will inevitably sooner or later happen that we end up here again. That's not a bad thing, that's normal things that happen. And it doesn't, the essence of that is live with failures. Don't try to avoid them. Embrace them. Take them into account in your design. And that's basically one of the essence or one of the key points of resilient design. Now a few words about what are complex systems, or where does the systems complexity come from? One big thing is, or one thing that is very, very important in systems is the system state. System state can be scattered and distributed overall. There are different kinds of states. There is state that is just temporarily. There is state that can be easily recalculated, like entries in a cache. There are states that can still be recalculated, but it needs more effort, like a calculation that is requiring 1 hour performance time to get calculated. That's all not that severe if you lose that, because it can re-establish and recalculate it. But you have also persistent state, like user input. You don't want to lose that. And combining that state with the different components where state actually is distributed in your system, and you want to then have one single view on the system, what is the state of the overall system? I would say simply not possible. So we must handle this kind of problem somehow differently. And out of that is a second sentence that's quite interesting. When you look at the big systems, let's say you imagine systems you have, even you don't need microsystems or microservices for that. You can have some normal monolithic systems. And you look in your log files. I would say if somebody here, not in any of the log files, has some exceptional error messages, I invite him honestly for a big coffee. I never have seen that. It's full of exceptions. Even severe ones could be there because the monitoring tools do not work. Everything is there, but for the user still everything works. But most of the complex systems, they run somehow always in degraded mode. There is more or less always something broken. Always that. It's not a bad thing. It's just reality. So we should cope with that kind of reality. That's what I said before about state. What kind of state is there? We have static state, like the config files. I did not mention that. Scratch data, dynamic data, especially the non-recomputable one, that is important. And now, think about how typically our state management traditionally looks like. We have a system where we just have that blue components. Now there comes a user, makes a request. The request goes ahead, along, creates state in other components. And now here's the explosion, and these things are blown up completely. And at the end, the state is gone, completely aware. The user everything is thrown back to the user, and that's one thing that we definitely would like to avoid. Now you could say, but this one was the one that exploded, so we have a root cause. But is that really really a good way to approach the problem? Because of course you can say this was this component that was originally the one that exploded first. But I would say the second component could say, if I am prepared that the other components can explode. So I could handle that. It's not necessary that all the failure is propagating through all the system. So it makes no sense to just point to and to look for some root cause. It would be better to invest the time and think about how we could embrace the failures in the other components so that it's not get propagated. So failure management and failure tolerance, it's a design issue. It's nothing that just happens. You have to think about. And this kind of state management definitely is broken. It's broken due to several reasons. We look at some of the patterns. One of the reasons is that the execution context here is temporarily bound. We have a coupling issue here. That also is part of the bad things that happen. And that leads us now more to the design. First, it's not a question when we are talking about design, what I mean with design. Basically, just simply said, we have number of components that make up our system, and they provide some services to the users or to the ones that use in the system, and they have to communicate internally somehow to achieve that. And now the question is, how should these things interact? Which rules? Where problems could arise and where not? And again, first thing is, resilience is by design. That's an interesting example. That was a hurricane happening, and before that, the whole coast here there was lots more houses were there, and that was the single house that was built up to stand a hurricane. I would say exercise worked. This is a good example by resilience is design. So we have to manage failures. An exception is not a failure, it's just a normal, natural state of our system, which should be modeled and managed. Now, first of the pattern is called crash only, meaning it's normal that a component can crash. It's okay. It should be possible. If you isolate it somehow, it's not that severe. So we need strong modularity between the different components. Component boundaries, you have an interface, how to call it, that's okay, but all the rest is hidden. Matches perfectly with microservices. But basically, it's about modularization. It's nothing new. Communication, yeah, if I call it somehow and wait for a result and the guy gives me never an answer, perhaps I should and use some timeouts. If I allocate resources for doing my stuff and my counterparts do not respond me with the answers, it would be good that after some time resources get freed again to avoid logs. And second thing is the request itself should be self-describing, because when I have a request that contains all the information, I can store it somehow, I can save it, and I can, even if it's blown up the components, I can take back the request and try to re-execute it at a later stage. If it makes sense, of course. There are maybe requests where that makes no sense, because then time is over after some 5 minutes. The customer is not interested anymore of what he clicked 5 minutes ago. But normally, requests should be self-describing. And in that scene, crashing is basically nothing else than stopping a component, and recovering is basically I started. And one thing why this is important is because it allows us to escape from a state where we have not really control what's happening. We have a non-deterministic block of something that's inconsistent somehow. We do not know why. But we can simply restart it, and normally, that's the assumption, it will work again. It will free up logs, it will reinitialize all the internal structures, even if you have, for example, some programming errors happening. It could be that restart solves the problem for another 2 or 3 days, depending on how severe the issue is. But it helps you, because you can continue operating even you have failures in your code. Example for such things, of course, life is the starvation things, deadlocks, timeouts, inconsistent state because you have stopped forcibly a Java thread, for example, memory issues, something like that. Typically, you have a memory issues in Java, you're dead. But we do not necessarily need to crash things. We can also say, perhaps it's better not to wait as a component just until I crash myself because I have overload or something like that. I can simply say, no, sorry colleague, I have too much work now, I cannot answer your request. So a component must be designed to take no from its counterparts. And on the other side, a component can say no to a service request. Of course, if possible, the component should answer the request and make its work. But it can, when it's necessary, also just say no. And the caller has to see how we can cope with that. For example, reduce fidelity somehow. Retry later. Wait. It's just a design issue. Next point is restartability. We already have, I also mentioned isolation. Now, looking at things like restarting stuff, that's okay, but if I restart something and I have some references to it, and references get perhaps invalidated, then I have not really won anything. So it must be possible that I can restart components completely isolated from the rest. That means I can restart it whenever I like. It should be transparent to my clients. That means also I can run it in any context, because it could be that I have to restart a component because the surrounding runtime context is blown up somehow. So I must have the possibility to restart it at another runtime context. From a client programming model, it should also not make a difference if it's running in process or out process, if possible. And the same thing is, of course, then if it's run on the same machine or somewhere else in the cloud. We're just talking about that the answers coming back. Of course, when you have networks in between, you have latency, something like that, more routing added or something like that. But that makes basically the crash-only pattern really powerful and matches quite that what you have with bulkheads in the ship construction, for example. And one way of prevent cascading failures to cascade also has a dependency on how you communicate. If you share synchronously things and you call it, and there is an error coming, or there is no answer coming back, you have to decide, should I wait longer or not? Or if at least you directly need that answer, then you have a coupling on time, typically also on the thread context. It's regardless if that's the same thread or in different machines. It's like the same with a local process and a distributed transaction. But you have a coupling there, which typically let failures propagate. If you do it differently, for example, you do the communication asynchronously, you just write the queue. And the other stakeholder there, the other component, can answer that request when it lags, and writing an answer queue, for example. Or if it fails, writing an error queue, or dead letter queue, or whatever. But basically one advantage is it does not propagate the failure directly. Of course, you are still getting a few other problems, because now you're just filling up queues. And then the next question is, who does control and get aware that something is getting wrong in your system? Which leads me to the next part, supervision. So we need supervision mechanisms to control what's happening. That could be the entry point where everything of the process started, as we have also seen by Neil Ford before. But that could be also some external processes monitoring things. Important is that it's not sufficient to only manage the monitor the components. You basically also need to monitor the communication paths in between, which is much more simpler with queues as when you do it with synchronous communication. Because if a queue fills up, that could be a good sign that you have to scale out in the back because the load is bigger. Another pattern is the minimal error kernel pattern. We have seen before state. And that state, we have seen that there is state that is important and state that is not so important. So it makes sense that the critical state actually is managed in a way, in a central part, in a kernel part of our architecture, which is protected through layers, that it's not broken. So our critical state is safe. And all operations that are more critical or more dangerous are delegated to layers more outside, which is then called that onion layer architecture style. Now, when we think about that and get that in action, you can say, okay, we have now layers, kernel, we have different state, persistent state, reproducible state, cached state, we have supervision in place, assuming that just the inner functionality level kernels are supervising the outer ones. That's not necessarily, must not necessarily always be the case. We can also go along the call path and different other states, just assuming it. Then we have a user doing a request, which then creates state. That state is transferred to the inner circle where it is safe, where it is stored. And now, basically, the user interaction, it's stored. We know that user has called that action X, Y, Z. And we can then continue handling it and managing whatever is needed in the outer layers. If now something blows up here, to whatever reason, and even this one still also blows up, nothing happens. It's not nothing bad because the critical state is still there. So we can restart the components and just re-execute the whole process again. It should work. We could then do that on another machine, on another node, whatever. The question is that enough? One thing that also is important, how we then manage failures. I do the question, I come back later. And because when we have a failure, we have an exception, we have some entry in a log, how we should manage that kind of failure. Possibly it's not enough to just write in a log file or throw in an exception. Especially, it's not necessarily written that a failure must be handled by the same component that is doing the call. Especially with asynchronous messaging in place, I can just send a message to some event queue. Some other component is trying to handle that message and the failure occurs. It must not be the same component that is handling the failure. It could be something else. So that means also that I have to model the failures in a way and handle the failures in a way so they can be managed and handled by the components that are responsible for dealing with failures. So a failure should be contained, have all the information in it so I know what's happening or what is happening in a bad way. It basically should be verifiable, somehow signaled so that somebody that is listening or should handle failures gets aware of that a failure was happening. Of course, there must be somebody that observes that kind of failure, and that means overall we have to manage a failure. We have to define it, that it could happen, and we have to be aware of which component of the system does handle it. And when we combine that so far, We have components that can crash. We can isolate, run them in an isolated mode. We can restart them. We have supervision in place. We have that minimal kernel design, correct state management, and we have failures that really are modeled correctly and also observed. Is the question, is that enough that our systems are self-healing? I would say we are already quite close. But coming back to that people, I asked if that is that enough what we have there, inclusive of now the improved failure management. And there's one thing that we have forgotten. This one still works. But this case, we have forgotten. There could be a failure that tears down your whole environment completely, because your whole data center goes down. It's not just a node or a machine or a microservice per se, it's everything that goes down. We forgot diversity and redundancy. Meaning you can never run a resilient system on a single node. You have to run it redundantly. You have to be replicated or redundant on your state, on your components. On the component side, I would say the state is more important, because when you have, for example, a distributed storage, you can easily start some components in other locations, in other areas, transparently, setting up on the same state again and just continuing with the work that you have had before. But to all that work, of course, you must then also have service location and load balancing to work. And basically also that must be replicated or redundant, or at least the state that is needed for service location and load balancing must be then redundant. And that's what typically also happens in things, in systems like Kubernetes and all that stuff. Typically it's etcd, Consul, that kind of services that basically do the distributed configuration management and configuration store that is used by these systems. And that's why they are easily restartable, and they still know where all the nodes and tiny bits of the whole systems are running when they crash. So, being that, still the question, is that enough? We have network communication between. We just talked so long about network communication that it could perhaps break or something like that, but unfortunately the network is a real issue when you talk about resilience. So basically we need complete decoupling in time and space. That's quite a lot. Because resilient also regarding that then affects the communication. Already mentioned synchronous versus asynchronous, but basically asynchronous is as a base communication style is definitely preferred when talking about resilient design. That does not mean that everything must also look asynchronously. It's also a question of how it works in the back. When you look at Okta, for example, it's somehow quite transparent that things are happening asynchronously there. But we must not only be tolerant against that something is timeout or a request is coming back or that I cannot reach a component. We have much more ugly stuff with network. Messages could be lost, reordered, duplicated. In that case, there is another concept. Remember me also about the base we have seen from Neil this morning, which is AC2.0, which is not the database one. I mean our messages sent out and traveling to our systems. They should be associative, commutative, idempotent, and distributed. That's, I would say, most of the part on the high-level architectural level. Now, when we go more, let's say, a bit deeper, Within what we can do, for example, within one single component, there are things there. For example, one thing is retry on failure. I call something, my component that I'm calling is returning some error. Then I can decide, depending on the answer, should I retry it? How fast should I retry it? Or should I blow up, throw some exception or whatever is needed? Or should I just, I can retry it later, or I can blow up directly, depending also on the answer. Because perhaps I know from the answer, okay, we have a severe issue, then it's useless to just try it again. Or I have an answer where I say, oh, I think she has a bit of stress, let's try it 30 seconds again. Then I can perhaps then resolve that problem within my components without having to escalate to the whole failure management in the overall system. Second part, if I don't get any answer, or we can even say if the answer is not coming back fast enough, I can say, okay, I have a timeout. Also then I have to decide, should I fail? Should I try a workaround, or should I try again later? In case of that I know that the other components has an issue, I already know that before I call that. Perhaps I don't call it and directly performs my workaround action. Or if I also have a failure, it's combinable with the former pattern. I have a failure and say, okay, I do not escalate that also to the outside. I just do an alternative action. I have foreseen that I can do something alternatively. Could be, for example, writing my request to some queue, knowing that this queue also will be handled somewhere later. Of course, I can also then cache results. So I don't have to call my components every time, because I know already if the results are recomputable, I can cache it and I can reduce with that the number of calls I have to do. And additionally, probably I'm quite faster in answering the request. Then the circuit breaker, quite a known pattern, I would say. It's basically the same with the power in your house. If you have some short circuit in your house, typically the whole power is cut down and nothing more works anymore. And in that case is that if you have a component that you can define that and configure that typically, has problems a number of times or for some time regularly for a certain duration, you just say, okay, there is an issue. I just try to give the component the chance to recover itself by not calling it anymore for some certain time. After that time is over, or any other kind of condition notification is coming back to me that I know, okay, I can try it again, I don't call it directly again. If it's there or some time it is over, I call it again, and hopefully the component then is ready to answer me. That can be built in automatically. For example, Netflix has quite nice mechanisms here. That's already similar to another one, fail fast. If I know that there is a problem, don't call, just try directly to manage the failure. Then the governor is another pattern, which is that I know that some downstream components have some limits, some capacity limits, some rate call limits. So I do throttle what I really call to them. One mechanism is also if you have use caching for that, because I don't have to call it every time, but it requires that you can produce enough significant cache hits that makes sense. That's also a mechanism. That are basically the most important patterns around resilience. Question is then, how do I test resilient systems? Basically, you should blow things up. So meaning, you should do whatever you think could break your system. If it's resilient, and there are then stages of craziness you can do, but if it's resilient, it should self-heal. If you send a kill -9 to some process, the process should be respawned. If you send data that is not valid, it should end up in some queues. If you load it with lots of loads, it should add additional components, handle the work, or then even reduce fidelity by say, no, I cannot answer that anymore. I have already enough load. Something like that. Something should happen. And if it does not happen, you can then analyze your system and see what was going wrong and improve it and try your test again. Of course, you can also the same do with network stuff. You can add intermediates that simulate failures that could happen in network area, duplicating messages. Let messages disappear completely. Defer messages. Whatever you like. But the question is still, when is a system finally then resilient? The answer is there is no clear definition. It depends. It depends on what you want to achieve. It makes no sense, even when you see all the mechanisms and patterns you have seen, there are some patterns that are nicely covered by modern architectures, what you have with cloud, with Kubernetes and containers, and what you can do there, like failover and automatic failover and something like that. Caching, we can introduce some more or less also with such mechanisms easily. There are different things we can get easily there. But for the more complex things, which within your business processes where things can go wrong, you typically have to make changes in your code. And it depends, of course, then it makes no sense to make your complete architecture resilient. You will not achieve that. It costs too much. You have to decide where you want to add resiliency, to what extent. And then you should try to think and analyze which components, where you want to start and you want to add such features. You should test it, and if you are satisfied and you say, okay, that's enough for me, that's okay, then stop. And one thing is that's done by Netflix and effectively that way, that if you try to run things and the tests, run them, if you are good enough, you can run them in production. Because you already know that your system is so resilient that it will not go down. It will be a bit slower, but you can really have the effects in production, and you have then not the problem that your test environment may not really be the same as the production environment. But that's definitely, I would say, the last step. Now, in practice, I would say you have, for doing something in practice, I would say there are 3 levels. First level is strategy. You have, as I said, you have to decide where in your architecture you want to be more resilient, to what extent, and to what cost. With all the side preconditions you have in mind, which products, which compliance you have to fulfill, the technology that already is in place, the market pressure that is around, the regions where you have deployments and stuff running, the overall enterprise architecture, your DevOps culture, for example, everything could be affected. It's not an easy task. The same with infrastructure. It's like with microservices. I would say if you can achieve things within resilient behavior with just by improving your infrastructure, going, for example, the same path as you could achieve with microservices, using some orchestration, some container services, and that DevOps related tool chains and everything, go that path, and you will have new flexibility to be more resilient out of the box. You just have to use it, and also then make it available and aware to your developers that do the stuff at the end. And if you have more, let's say, silos organizations where your infrastructure is in its own organizational unit, talk with them that they, if they're not already there, get more flexible, that you can deploy other things or additional things and not are not constrained to what you have, that you have some kind of preconditions that you can do things more resilient. Because we have seen only a few patterns are really the ones that you can do in your code yourself. They maybe also help you, even if you have a monolith building up on different components. You can have single components where you can improve the components to be more resilient, and that could help for the overall robustness of your solution. But also there, you have to analyze if you're really then improving the right places in your monolith to really achieve the results that you want to have for the overall solution. And then finally, of course, you have then the stuff in the applications, where the question is which programming languages have you in place, which frameworks, how is service discovery working, it's doing by infrastructure, is there some components running in code itself, what is there? Monitoring, how is monitoring in place, which third-party products you have, everything else. And summarizing, when you look at the stack of tools, I would say lots of the things that also could be achieved by going towards microservice path, by going the DevOps path with more automation on the infrastructure side, I would say it leads you automatically also much more to have preconditions for building systems overall also more resilient. But that alone is not enough. For real resiliency, you have to take in account into your design of your applications. And for that is not possible for everything. You have to decide which applications and which area should profit from that kind of architectural thinking and which are not. There are a few of things, again, of frameworks also in the Java space, which also help you build things more isolated, which also help you with organizing communications in queues, also within your code. You don't want everything then to go out to some external message queuing system, something that also within a monolith you can have queues and organize things within that. OCCAP, for example, is a platform that has more or less every resilience feature built in out of the box. You can use that for parts of your solution, for example, for replacing parts of your logic. You can also use Vertex with its distributed service bus, which would help you lots of things, but you still have to decide where it makes sense and to what extent you want to do that. What's definitely the case is that infrastructure could help you a lot, and in my opinion, it would be a good starting point, because things are rather complex, and I would recommend that not writing stuff that you don't need to write yourself. Don't write it yourself, especially in that technical infrastructure area. It's getting rather quickly much complex. So summarizing, remember, complex systems run always in degraded mode. Complex systems run as broken systems. And resilience is a design question. That's from my side. I hope you have some ideas to get around and to have additional input what it means to build a resilient system. It is quite an abstract talk. There's not much technical stuff in it. Questions? If not, I thank you very much for listening. Have a nice afternoon.